Okay, so today we're going to talk about, once again, more about properties of a derivative, and more importantly, the derivative itself ends up being pretty much a function. So if you notice so far, in fact, let's focus on last section. So we could say that last section, we found the derivative of a function f at a fixed number. And let's call that number a. So if you remember, this is what we did last section. We found a derivative at a fixed number a. And in fact, if you remember, I myself said it's better to find the derivative in a generalized form. If you remember, instead of finding the derivative at a specific number, we found it at a, and then we plugged in the specifics of a. So it's kind of like we're headed towards what we're doing now anyway. So instead, what we're going to do now is, instead of finding derivatives just in terms of a, or in terms of just a number like 2, 3, 4, we're going to find them in terms of x, or whatever the variable of our function is. And then we can go into specifics and then plug them in. And what we'll notice is that the derivative itself becomes a function. So this is where we're kind of getting into a little more in depth with derivatives, where we're saying, look, I could find the derivative of a function, and not only can I find the derivative of a function, that in itself becomes a function of its own. So we're going to start seeing some relationships between functions and derivatives and so on. So what we're going to do now is we're going to say, let us now consider the derivative of a function f as a function of x. That is, I'm interested in finding f prime of x. If you remember yesterday or in the last section, we said f prime of a. So now we're going to go into f prime of x, which, in other words, that is the following. We're going to define f prime of x as the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, and so notice how what I'm doing is I'm still using the same definition as we've always used. However, instead of plugging in a here or a specific number, I'm calling it x. Now, what happens is, look, if f is a function of x, and f prime also could be expressed as a function of x. So we're basically saying, look, the derivative is in fact in itself a function. So we can say, thus, given any number x such that the limit exists we assign to x the number f prime of x. So basically we're saying, look, if this limit exists for f, then this limit turns into f prime of x. That's basically what we're saying here. So let me make a couple of comments, and then we will do a couple of examples, and then we'll move on to a few theorems that we need to deal with. So here's what we could say. We could say, look, f prime of x is regarded as a new function called the derivative of f of x. Okay, so that's the first comment I want to make here. So what you notice is f prime is a new function of its own. However, it's also known as the derivative of f. So there's two things going on. See, we've learned in earlier sections that, look, the derivative of f is, in other words, the slopes of the tangent lines of f, right? Which that's still true. So f prime, not only is it the derivative of f, it's the slopes of the tangents of f at each x value, and it's also the instantaneous rate of change of f. Okay, so these all mean the same thing. So the second comment I want to make, which this is going to be important for graphs. So for graphs, and we'll talk about that in a minute, is f prime of x represents the slopes of the tangent lines of f at each, let's call it f of x at each x value. So what am I basically saying here? In other words, for example, the slope of each tangent is the same thing as saying it's the value of f prime of x. Okay? And let's call the slope of each tangent of f of x. So what I'm saying is, if I take the slope of the tangent of f of x, that's going to give me the y value of my derivative at that x value. Okay, so graphically speaking, that's kind of what we're going to look at. So take a minute and let this sink in. What I'm saying is, if I draw the graph of f, the slopes of the tangents of f at each x value will represent the y values of the derivative, because after all, f prime is the slope of the tangent of f. So basically, since f prime is in itself, if you think about it, this is another y value, isn't it? It's saying, you tell me what, for each x, plug it in here, this will give you the y value of the derivative. How do I describe the y value of the derivative? That's pretty much the slope of the tangent of f. Okay, so that's going to be helpful in this first example that we do. So, and don't hesitate to ask me questions if you have any regarding this, because sometimes it may take a little bit of time to figure out exactly what's going on. Okay, so here's what we're going to say. We're going to say the graph of a function f is given. Okay, so I'm going to give you the graph of f, and we're going to use that to sketch its derivative. Okay, so I'm going to draw this kind of large just so we can be clear as to how we would approach this. So if I draw my graph, here's what f is going to look like. So okay, so here's the graph of f. So this is f of x. And what I want to do is I want to sketch its derivative. Okay, so now remember, what did I tell you earlier? How do I find the derivative of a function? Well, geometrically speaking, or graphically speaking, what do we know? The slopes of the tangent of f basically describes the derivative of f. And in other words, the slope of the tangent at each x value of this function gives me the y value of the derivative at each x value. So the easiest slopes to find, or the ones that you want to go after first, are the ones where we have horizontal tangents. And just by looking at this graph, you could see where my horizontal tangents are. I have a horizontal tangent at this x value, okay? I have another horizontal tangent at this x value, and finally, I have my last horizontal tangent at this x value. Now remember, this graph that we're sketching of f prime is a sketch, okay? So yours might look slightly different than mine, okay, depending on how far up or low you go when you're sketching these graphs, but you know, as long as they're good enough, we're happy with it. So no, look at this. At this x value, whatever this x value may be, what do you notice? The slope of the tangent is so let's label these guys. These are my x values, where my slopes of the tangents are 0. And if the slope of the tangent is 0, what does that mean? The y value of my derivative at these tangents would be the same as their slope. And we know horizontal lines have slopes of 0. So at this x value, my derivative is going to have a y value of 0 because my slope has or my tangent has a slope of 0. Same thing here. My tangent has a slope of 0. For this x value, my derivative is going to have a y value of 0. Remember, the slopes of the tangents of f tell me the y value of the derivative at those x values. So I have a 0 here as well. Okay, so that takes care of the easy part. Now comes the hard part. And here's where you might need a little time to let this kind of sink in. But let's start from the left and move to the right. Or let's start from this tangent that's horizontal. What if I move to the left? What do you notice happens to the slope of my tangent here at that x value? You notice that we have a positive slope. And see, here's where you'd kind of have to estimate. So if you were to say, look, what is the slope of this? The slope of this is, let's call the slope of this tangent 1. So what does that mean? If the slope of this tangent is 1, at this x value, my derivative is going to have a y value of 1. So wherever y equals 1 is, which is basically, let's call that 1, what I notice is I'll have a point right there. And then what happens if I go further to the left? Let me go a little further to the left. What do you notice happens to your slope? At this x value, the slope becomes even steeper. So let's pretend, I don't know, this slope is 3, for example. Okay? I hope you get the idea here. So my y value at this x value, the derivative will be 3. So you'd basically say, here it is. Here's the point. Okay, there is my point. Okay, so what do you notice is happening to this graph? As I go to the left, the slopes of my tangents become steeper and steeper. Which, what does that mean about the y values of my derivative? My y values of the derivative, since the slopes become steeper, and they're positive steeper, my y values become larger and larger and larger. So I could see that my derivative, when I go to the left, looks something like that. Okay, so far I've drawn this part of my derivative. So we use the same reasoning here. What do you notice here? As I move to the right, what happens to my y values? My y values become, or my slopes of my tangents become, they're negative and they get steeper and steeper, and then at some point they're less steep and they get closer and closer to 0. So we do the same thing. So let's say if this has a y value or a slope of -0.5, at this x value, my derivative will have a y value of -0.5. And then it'll become a little steeper here. And then at some point here, it just kind of loses its steepness. It becomes less steep, which means it's going back to 0. So if you notice what's happening is my slopes are negative, they get steeper, which means my graph goes further down, and then it has a turning point and it goes up. So it kind of looks like this. Now here's where your graph might look different than mine. You might go further down and come up, which it doesn't matter as long as we're close enough. So then using that same reasoning, what happens to my slopes of the tangent as I move to the right? They're positive, they get steeper, steeper, steeper. And then as they get steeper, what does that mean? My y values become larger. And then at some point, it has to level back down to 0. So the slopes of my tangent become less steep and they get closer and closer to 0. So what this is going to look like is it's going to go up and it's going to come back down. Okay, so notice how my graph of the derivative so far looks something like this. okay? And then what happens from this point on, if you look at your derivatives, they are negative, and they get steeper and steeper as you go further down. So the steeper it becomes, that means the more negative it becomes. So from this point on, the graph of f goes down. So basically, I just sketched the graph of f prime by looking at the graph of f. Okay, so hopefully it makes sense. Now remember, the key here is the slopes of the tangent, the steepness gives me the y value of f prime, and that's basically what I did. Now you don't have to. I know at the beginning I kind of plotted some points, but later on I didn't. But the reason why I plotted these points is because I want you to kind of make the connection. Whatever this slope is, the derivative has that y value. So of course, this is steeper than that, so this is going to have a smaller y value, and then at some point it becomes less steep, which means my y values get closer to 0. Okay, so we basically graphed the derivative by looking at the graph of f. Okay, so you'll have plenty of practice with this stuff, but don't hesitate to ask me questions if you have any. So let's move on to example 2. And this one is more straightforward, or it's along the lines of what we've been doing pretty much the last few sections. So we could say if f of x is the square root of x minus 1, find the derivative of f, and then state the domain of f prime. And we could do that after all, since it's a function of its own. So remember, when we find derivatives of functions from this point on, we're going to find them with respect to whatever the variable is. So since the variable of f is x, I'm going to find a derivative with respect to x. Okay, so remember, we'll plug in specifics later. So if I say what's f prime of 2, well, I don't care about what f prime of 2 is. I'm first going to find f prime of x, and then I'm going to plug in 2 for x. Okay, so generalizing is much better because it allows us to be, to get a formula that describes all the possible scenarios and cases. Okay, so let's do this. We have f prime of x, by definition, will be limit as h approaches 0 of f of x plus h minus f of x all over h. So then what does that give us? That gives us the limit as h approaches 0 of square root of x plus h minus 1 minus square root of x minus 1 all over h. Okay, so now if you remember, we're kind of stuck here. What's the trick? And I'm sure you should be pretty good with limits when you have square roots, and especially if you have two terms. We will use the trick of conjugates. So multiply top and bottom by x plus h minus 1 plus x minus 1. I'm running out of room here, but this is just a conjugate of that. So square root of x plus h minus 1 plus square root of x minus 1. Now remember, my goal is to cancel out this h, so I'm better off not multiplying the denominator out. I'll multiply the numerator out, but leave the denominator as is. So this becomes the limit as h approaches 0. Now remember, since they're conjugates, all I really care to do are multiply the first and last terms. The middle terms are going to cancel out, so I really don't care much for them. So the top will be x plus h minus 1, because that times that will give me x plus h minus 1. And then negative rad x minus 1 times positive rad x minus 1 will just give me minus x minus 1. Now I just put parentheses around this, make sure this negative belongs to this whole thing, or it distributes. And then the bottom becomes h times square root of x plus h minus 1 plus square root of x minus 1. Okay, so now let's simplify the top. Limit as h approaches 0. So what do I have? X, when I distribute this negative, it'll be x minus x, so the x's will cancel out. And then I have negative 1 minus negative 1, which this will be negative 1 plus 1. So the x's cancel and the 1's will cancel out as well, because once you distribute the negative. So what am I left with on top? Just an h, which is good news, because that's what we needed to cancel out this h. So it'll be square root of x plus h minus 1 plus square root of x minus 1. So now cancel out the h's. So 1 plus square root of x minus 1 plus square root of x minus 1 will just give me minus x minus 1. And then negative rad x minus 1 times positive rad x minus 1 will just give me minus x minus 1. So now cancel out the h's. And now we have the limit as h approaches 0 of 1 over square root of x plus h minus 1 plus square root of x minus 1. And now I could finally plug in 0 for h. And if I do that, I get 1 over square root of x minus 1 plus square root of x minus 1. Okay, and that gives me 1 over 2 square root of x minus 1. And there you have it. And notice how this is in fact a function of its own. So what we're saying is, so f prime of x is 1 over 2 rad x minus 1. And notice how not only is this the derivative of that guy, which is f, it's also a function of its own. Okay, and so what is the domain of this guy? The domain, if you think about it, what is it that we want? I don't want my denominator to be 0, and I don't want x minus 1 to be negative because I'm inside the square root. So what we really want is x minus 1 to be greater than 0, which basically this implies x has to be greater than 1. So the domain of this guy is from 1 to infinity. And so what did you notice, by the way? Compare the domain of the derivative to the domain of the function. What is the domain of the original function? It's 1 to infinity, including 1. But this one is 1 to infinity, not including 1. So is that a coincidence that whenever this guy's not defined, the derivative doesn't exist? And the answer is, of course not. Because remember, how do you describe the derivative? They're the slopes of the tangent lines of f. So if this guy's not defined, it has no slope of tangents. So if this guy's not defined, then clearly this guy's not defined. But also remember that just because f is defined, it doesn't mean that f prime will be defined. In fact, the only place where we can make that statement is f prime isn't defined at 1, but f is. But just keep that in mind, that the domain of the derivative will be potentially the same as the domain of f, or it may be even less than the domain of f. Okay, so let's move on to a couple of some other comments I want to make here. So now this is just for notation purposes. So other ways of expressing derivatives are given as follows. So these are just different ways of saying, hey, this is find the derivative, okay? And I'll tell you which ones are the most important ones. So if x is the independent variable and y is the dependent variable, then these all mean the same thing. So the one that's common is you've seen f prime of x, right? Which we're saying the derivative of f with respect to x. You could also say y prime, okay? They mean the same thing. And of course, f of x and y are the same thing anyway. And then you could have dy dx. And see, this is in Leibniz notation, which basically when you see dy dx, you're saying find the derivative of y with respect to x. Okay, so this is basically saying the same thing as that. And then you could have df dx, which y and f are the same thing. Or you could have dx of f of x, which that's basically saying find the derivative of f of x with respect to x. So remember, these all mean the same thing. So I'm just trying to point out that when you see this notation, in other words, these are all saying find the derivative of f with respect to x. And then you could have capital D f of x, this is called the differentiation operator. So which means find the derivative of f with respect to x. Or you could have capital D sub x of f of x, which this is basically saying the same thing as that. It's just being a little more specific. It's saying find the derivative with respect to x. So these all mean the same. In this class, I think this one that I'm underlining, this one, the ones that I've underlined, you're going to see more commonly than the other ones. Okay, so what I want to kind of also point out is that the symbols capital D and ddx are called differentiation operators. So in other words, when you see capital D or ddx, basically just saying you're going to be finding the derivative. Okay? So, and differentiation, we haven't really seen yet. I'm going to define what differentiation means. But anytime you see differentiation, in other words, it means derivative. Okay? So let's define that word. Let's define differentiation or differentiable, so we're kind of familiar with it. So by definition, we could say a function f is differentiable at a if f prime of a exists. So what are we saying? A function is differentiable at some number if f prime of a exists. So in other words, differentiable means the derivative exists at that value of the function. Okay, so for example, the first example we did, or the second example we did where we found the derivative, what do we notice? Let's go back to it real quick, which is right here. This is the derivative. See, this guy is not differentiable at 1. How come? Because the derivative doesn't exist at 1. It's not differentiable at 0 because this is undefined at 0. So this guy's what? Differentiable anywhere from 1 to infinity, not including 1, of course. Okay, so when we say differentiable, we're saying where does the derivative of this guy exist? So that's basically it is. So that's basically all it is. So we could say it is differentiable on an open interval from A to B if it is differentiable at every number in the interval. So for this one, we're saying, look, if you say it's differentiable from A to B, that means the derivative should exist everywhere between A and B. Okay, so when I tell you something is differentiable, in other words, I'm saying the derivative exists. Okay, so if I say a function is differentiable from negative infinity to infinity, what does that mean? The derivative is defined everywhere. Okay, so like I said, in example 2, that function that we found the derivative of, it was differentiable from 1 to infinity. Okay, so remember, when I ask you, is something differentiable, does that mean, then that means does the derivative exist? Okay, so let's look at this third example, which this is going to be a very important, or it's a nice result that kind of shows differentiability. So once again, we're dealing with the absolute value of x. So where is f of x differentiable? So once again, to find out where this is differentiable, I need to basically write this as a piecewise function, as I'm sure you've guessed. So here's what we know. We have f of x equals to x if x is greater than or equal to 0, and negative x if x is less than 0. So if you remember, by definition, how do we find the derivative? The derivative, by definition, isn't it a two-sided limit, right? Because if you think about it, what do we know? F prime of x equals to limit as h approaches 0 of f of x plus h minus f of x all over h. That's my derivative, which if you look at this, this is a two-sided limit. So for the derivative to exist, for this function, this two-sided limit has to exist. Now, if you look at this and see out of experience, what do you know? We know that two-sided limits, especially for piecewise functions, they're less likely to exist at values where when I transition from one function to the other. Other than that, like x, if I had just x, my two-sided limit should exist everywhere. So I shouldn't be too concerned about x. And same thing with negative x. But what I'm concerned about is at 0. So let's first focus on 0, okay? So we want to check for differentiability. Let's see, is this differentiable at x equals 0? And that's our question. So here's what we're going to do. We need to break this up into two parts, okay? So if x is greater than 0, what do we have, okay? Or we don't even need to do that. Let's just say this. So at x equals 0. So what do I want to find? I want to find out, does f prime of 0 exist? Yes or no? So this will be limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. Okay? So what does this break down to? Limit as h approaches 0 of f of h minus f of 0 all over h. Now notice how this makes a big difference, because this is saying go to your function f and plug in h for it. But if I'm to the left of 0, then I have to use the negative because I'm less than 0, right? Because if h is if I'm to the left of 0, if I plug that in here, I get a negative number in there. If I'm to the right of 0, I have to use that top one. So let's break this up into a two-sided limit. So here's what we're going to do. I'm continuing this down here. We would say the limit as h approaches 0 from the left side. What do I have? I have f of h minus f of 0 all over h. So if I'm approaching 0 from the left side, that means my h values are negative, aren't they? And if my h values are negative, which h is another way of talking, I mean, I'm plugging in my x value in here, aren't I? So what do I have? I have to use negative x. So what would this be? This would be limit as h goes to 0. So f of h becomes negative x. Instead, I'm replacing x with h. So it'll be negative h minus f of 0, which f of 0 is going to just be 0, all over h. Which notice what happens here. Then I get negative h over h, which those cancel out, and that gives me negative 1. Okay, now, what do I get for the limit as h goes to 0 from the right side? Once again, I have f of h minus f of 0 all over h. However, if I'm approaching 0 from the right side, f of h, instead of becoming negative h, now becomes positive h. So limit as h approaches 0 from the right side, this becomes h minus 0 over h, which then what do you notice? I get 1. So what happened here? This two-sided limit, does it exist, yes or no? And if you look at it, it doesn't exist. So what does that mean? This guy doesn't exist at that, so f of x is not differentiable at x equals 0. So the derivative doesn't exist at x equals to 0. Okay? So that was the key. Now, how do I show? Now the question is, well, how do I know if it's continuous or it's differentiable on the other values? So think of it this way. So now we showed that it's not differentiable at 0. But now the question is, well, we said, look, this guy, I've only shown that it's not differentiable at 0. Well, what if x is greater than 0? And what if x is less than 0? Is this guy differentiable, yes or no? And that is actually could be done simply, because if we say if x is greater than 0, then here's what we could do. We could say then f prime of x equals to what? The limit as h approaches 0 of f of x plus h minus f of x all over h. Now look, as long as x is greater than 0, h is a very small number. So here's what we're assuming. When you add or subtract a number that's close to 0 from x, you're still going to be greater than 0, okay? Because no matter what x is, I could always find the value to the, like for example, if x is 0.1, I could always find the value to the left of 0.1 that's still greater than 0, right? Like 0.01, so, and so on. So as long as x is greater than 0, what do I know? F of x plus h is going to be greater than 0 itself. So I could use, if you go back to the piecewise function, I'm going to use the one that's just x. So if x is greater than 0, f of x plus h becomes just x plus h. And then that becomes minus x all over h. And what does that give us? The x's cancel out and I have h over h, which just gives me 1. So what do I notice? As long as I'm to the right of 0, my derivative exists, and my derivative is always 1. Now, what if x is less than 0? Then f prime of x equals to the limit as h goes to 0 of f of x plus h minus f of x all over h. Now, if x is less than 0, the function I use for my piecewise, I use negative x. So this becomes what? Limit as h goes to 0 of negative x plus h minus negative x all over h. So this becomes limit as h approaches 0 of negative x minus h plus x all over h. So the x's will cancel out, and what do I have left? Negative h over h, which they cancel out, and I have negative 1. So what is this saying? And this makes sense, doesn't it? Because what is my derivative saying here? As long as I'm to the right of 0, my slope is always 1, the slope of the tangent, which, doesn't that make sense? Because we have a line that has a y, that's defined as y equals x, which the slope of that is always 1. And this is saying if you're to the left of 0, my absolute value function always has a slope of a tangent that's negative 1. So if I were to graph this, this is what happens. And notice how no matter what tangent I pick, as long as I'm to the right of 0, the slopes of my tangents are always 1. And if I'm to the left of 0, notice how the slopes of my tangents are always negative 1. And we could see what the problem is. Why is this not defined at 0? Because when I go to the left, my slopes are negative. When I go to the right, my slopes are positive. So my two-sided limit ceases to exist here because the slopes aren't agreeing. Okay, so that's what's kind of going on here. Whereas something like this, notice how the derivative exists here, because what do you notice? The slopes of my tangents are negative or positive to the left, and they're negative to the right. But as I get closer to this point, they become less steep. So from both sides, the slopes start agreeing. They both start going to 0. Okay, so that's kind of what's going on here. So here's this next theorem. And then after this theorem, we'll kind of wrap up this section. But this is actually, I'm going to put an asterisk with this theorem because this is very, very important. So this theorem pretty much connects differentiability to continuity. So here's what we could say. And this theorem is nice because we get a really nice result. Remember, we've noticed that when things are continuous, we get really nice results out of things. So here's what we could say. If f is differentiable, at a, then we could also say f is continuous at a. So what am I saying? If something is differentiable, then it's continuous, okay? Which, of course, if you look at this, if the slope of my tangent line exists here, then this function must be continuous there, which you could see it has no cuts or breaks, okay? But if the slope of my tangent doesn't exist there, it doesn't necessarily, if the slope of the tangent doesn't exist, then that means, like, for example, if I have something like this, I kind of have a break here. I can't draw one tangent that describes the graph because what is it? Is it this tangent or that tangent or so on? So, you know, if it's not, if f is differentiable, then we could say it's continuous. Now, my question to you is, and think about this before you answer it, is the converse true? In other words, what's the converse? If f is continuous, is it differentiable? And see, here's where we have to be careful. A lot of students make a mistake by saying, yes, it is. Because look, if it's differentiable and it's continuous, then that means if it's continuous, it must be differentiable. And the answer to this is actually no. In fact, the last example we did, we kind of showed it because didn't we show that absolute value? Look at the absolute value graph. Is this continuous everywhere? And the answer is yes, because it has no cuts or breaks. But is it differentiable everywhere? And the answer was no. Didn't we see that at 0, it wasn't differentiable? So what do we notice? Just because a function is continuous, it's not differentiable. You can't say it's guaranteed to be differentiable. But if it's differentiable, it's guaranteed to be continuous. So the converse isn't true because we can say take f of x equals to the absolute value of x at 0. Okay, what is it that we saw? It was continuous, but not differentiable. Okay, and we proved that in example 3. So this was continuous but not differentiable. So remember, from this point on, we can say, look, if a function is differentiable at some value, it's guaranteed to be continuous at that value. But just because a function is continuous at that value, it doesn't guarantee for it to be differentiable. Okay, so the last thing I want to talk about, which is just basically some cases where a function is not differentiable. Okay, so basically the first one is when we have kind of like a corner or a kink. So at x equals a, this function is not differentiable because, so what we have is a corner or a kink. Okay, so when you look at a graph, at corners and kinks, we don't have functions that are differentiable. How come? Because remember, by definition, a derivative is a two-sided limit. So what does that mean? If I were to say that this guy's differentiable at x equals a, what does that mean? The slopes of the tangent when I approach a from the left side should be the same as the slopes of the tangent when I approach a to the right side. But what do you notice? As I approach a from the left side, what happens to the slopes of my tangents? They're positive and they get a little steeper. Okay, and how about from the left side? The slopes of the tangents are negative and they get steeper. But what you notice is the slopes of the tangent to the left and to the right, they're never going to level off. In fact, as long as I'm to the left of a, the slopes of my tangents are always going to be positive. As long as I'm to the right of a, the slopes of the tangents are always going to be negative. So at this value, I can't say the slopes of the tangents are approaching the same thing because it's impossible. They're both kind of, one's positive, the other's negative. So you could see that graphically speaking, whenever we have a corner or a kink, we have a function that's not differentiable. And if you notice, the absolute value function, which was this guy, had a corner at 0. And when we showed it algebraically, we saw that the slopes to the left of 0 were always -1. To the right of 0 were always +1. They never start approaching the same slope. They never agree, unlike this one. See, this one, it's defined here. How come? Because although the slopes to the left are positive and the slopes to the right are negative, the closer you get to this point, the slope becomes less negative and less positive, and they both start approaching 0. So they're starting to agree with each other as you get close to this point. But over here, they never level off. They always stay the same. So that's what's going on. Okay, now back to the next case. When we have discontinuities. So we would say if you have something like this, or any kind of a discontinuity. So this doesn't have a slope of a tangent at a, which means the derivative doesn't exist at a. It's not differentiable. So we would say if it is discontinuous. So in fact, see, what did we say earlier? We said if a function is differentiable, it's continuous. Now what we could say is, look, we could think of it in terms of the contrapositive. If it's discontinuous, it's not differentiable. So we could say, in fact, if a function is discontinuous, at A, then f is not differentiable at A. Okay, so that we could say, that's a fact. So here's what we know. Differentiable means continuous. If it's discontinuous, it's not differentiable. But remember, we can't say if it's continuous, it's differentiable. Those we could run into problems because, once again, coming back to this corner or kink, this is definitely continuous at A, but it's not differentiable. Okay, so the last type of discontinuity we could have is if it looks something like this, which, what do you notice we have at A? We have a vertical tangent. And when you have a vertical tangent, what does that mean? The run, remember, tangent lines, the slopes are defined as rise over run. And if I have a vertical tangent, then that means my run is 0, which means I'm dividing by 0. So any vertical tangent, so a vertical tangent would mean that we have no derivative, or it's not differentiable at that value. So in other words, if you say, look, limit as x approaches A of f prime of x, and I took the absolute value because from the left side, these are negative or positive, and from the right side, they could be negative. It doesn't matter as long as we get infinity, which that means, in other words, it does not exist. So basically, in this case, f is not differentiable at A. So graphically speaking, there's 3 ways of identifying where a function does not have a derivative or it's not differentiable, which there are at corners and kinks, at discontinuities, and anywhere where you'd have a vertical tangent. Okay, so those are kind of like the visual representations. All right, so that pretty much takes care of this section.